This is the paper review for EE 531. The first paper that I reviewed was Accurate Uncertainties for Deep Learning using Calibrated Regression. So I'll first talk about the need for uncertainty, then I'll talk about Bayesian neural network as a mean to obtain uncertainty. Then I'll talk about the need for a calibrated uncertainty, and lastly I'll talk about the calibration algorithm for regression models that the paper proposed. So the reason why we need to model uncertainty is that deep neural networks tend to be overconfident about their predictions, and the inability of ANNs to say "I don't know" is problematic for application where silent failure can lead to dramatic outcomes. For example, self-driving cars, medical diagnosis, or finance. And Bayesian framework provides a way to analyze and train uncertainty-aware neural networks. So a Bayesian neural network is a stochastic artificial neural network trained using Bayesian inference. So instead of having a single weight value, they put a distribution on the weights. And they simulate multiple possible weights, thus they can be considered as a special case of ensemble learning. The main motivation of ensemble learning comes from the observation that large set of average performing but independent predictors can lead to better predictions than a single well-performing expert predictor. However, in Bayesian neural network, this is not their main goal. Rather, the neural network to obtain a better idea of uncertainty associated with the underlying process. So the typical Bayesian inference algorithm is that assuming you know the posterior p theta given d, one does not have to undergo a learning phase. We just sample from the posterior and do model averaging. So here, we first define a prior, and then given some data, we get the updated posterior. And from that, we sample the weights for multiple number of times. Here it's, so I equals 0 to n. So we do it n number of times, and we run through the network with the same input n times, and we get n outputs. And the prediction is the average of those n outputs, and the uncertainty can be calculated as this equation. And the good thing is that we can get the distribution of py given x. If you assume a Gaussian, the prediction value becomes the mean and the uncertainty value becomes the variance. However, generally calculating the posterior is generally intractable, so two widely used methods to overcome this problem is Markov chain Monte Carlo and variational inference. So uncertainty in regression setting is given by a credible interval, and the reason why we were able to get this credible interval was because we were able to get the conditional distribution y given x. And a credible interval is an interval within which an unobserved parameter value falls with a particular probability. So for example, for a 95% credible interval, we should expect that approximately 95% of our observed data fall inside the interval. However, we not only want a uncertainty measure, but we also want it to be calibrated. Calibrated uncertainty means that the credible interval aligns with the observed data. So for example, a 95% credible interval, but only 80% of the observed data falls within the interval, then the uncertainty value is not calibrated. And modern deep neural networks achieve higher accuracy but poor calibration compared to shallow networks. And this is known to be because of the width, depth, and batch norms. And in this kind of techniques, all negatively affects the calibration. Thus, in order for the uncertainty to be meaningful for the user, we need to calibrate the uncertainty, which is changing the credible interval so that it matches the true outcome. The proposed method that the paper proposes, the proposed calibration method that the author proposes is they extend the recalibration method used for classification tasks, such as plot scaling, to the regression task. And they propose a procedure that is universally applicable to any regression model, and it does not require modification of the model, and the algorithm is applied to the output of any existing model in the post-processing step. So the algorithm has two main steps. They first construct a recalibration dataset, and then they train a model, regression model on this. And I'll go in a step-by-step detail. So the first step of the calibration algorithm is to obtain predictive conditional distribution for each x in the calibration set. So for each data in the calibration set, BNN, the Bayesian neural network allowed us to get the distribution Py given x. So we can calculate the CDF of the distribution. Then the observed y of each data point, denoted by yt, falls somewhere within those conditional distribution, and we evaluate the conditional CDFs at each observed value of the y to obtain the predicted quantiles. So for each data in the calibration set, so for example, if y0 falls here, we can get the value of the CDF, and we do that for all of our calibration set. We next find the empirical quantiles, which are defined as the proportion of observations that have lower quantile values than that of the current observation. The mapping of the predicted quantiles to empirical quantiles will form a recalibration dataset. So put it simply, we set all the values that we found in step 1a as the x-axis value. Then for each one of them, we find out how many observed data in our calibration set would be in that credible interval. So for example, if the x-axis value is 95%, 0.95, but we observe that only 0.8 calibration set fall below the credible interval set by that 90% credible interval, then our y-axis corresponding to the x will be 0.8. We then train a regression model on the recalibration dataset and use it to output the actual probability of any given interval. So for example, if p equals 95%, but only 80 out of 100 observed yt fall below the 95% quantile, then we adjust the 95% quantile to be 80%. So it will be as if we are increasing the credible interval. One other concept that the author introduced is the sharpness. And sharpness is telling us how useful the predictive interval is. That is, how wide it is. If it is excessively wide, it does not allow any meaningful inference, even though it is well calibrated. The second paper that I reviewed was PC-Fairnes, a unified framework for measuring causality-based fairness. So, the fair machine learning studies how to develop predictive machine learning models such that decisions made fairly treat all groups of people irrespective of their protected attributes such as gender and race. A recent trend is to define fairness as causality-based notions, which concern the causal connection between protected attributes and decisions. There have been a number of causality-based fairness notions that have been proposed for capturing fairness, such as total effect on intervention, direct-indirect discrimination on path-specific effects, counterfactual fairness on counterfactual effect. The limitation is that it is the identifiability, that is, whether they can be uniquely measured from observational data. And causality-based fairness notions are defined based on different types of causal effect, and thus their identifiability depends on the identifiability of these causal effects. And the paper proposes a framework for handling different causality-based fairness notions. So, for some definitions, background, so if we have a causal graph where S is the protected attribute, Y is our decision, and all the white nodes are non-protected attributes, um, we can define the total causal effect as the follows. The total causal effect of the value change of S from S0 to S1 on Y is defined as this equation. Then path specific effect is that given a causal path pi, the path specific effect of the value change of S on Y through that path is given by this equation. And the counterfactual effect is the given a factual condition, the counterfactual effect of value change from S on Y is given by this equation. The proposed fairness measure, they first define a path-specific counterfactual effect. So given a factual condition and a causal path, the path-specific counterfactual effect of the value change of S on Y through that path is given by this. And the path-specific counterfactual fairness, which is called the PC-Fairnes, is that they are trying to given a factual condition O and a causal path, the predictor achieve PC-Fairness if the path-specific counterfactual effect equals 0. We also say that it achieves the thou PC-Fairness if this value is the absolute value is less than or equal to thou. So in this section, the author defined a unified fairness notion for representing different causality-based fairness notions, and the key component of their notion is a general representation of causal effects. In table 1, they show that previous causality-based fairness notion can be expressed as a special case of the PC-Fairness, and in addition, the notion of PC-Fairness also resolve new types of fairness that previous notions cannot. One example is this individual direct discrimination. So to measure this path-specific counterfactual fairness, they first introduce something called response function variables. Response function variables to parameterize the causal model. So in general, exogenous variables can be variable of any type with any domain size, making the causal model difficult to handle. However, for particular values of exogenous variables, the functional mapping for each endogenous variable is deterministic. Thus, we can map each value of uv to a deterministic response function rv. And this equation shows that. And the paper shows how the joint distribution of all the endogenous variables PV can be expressed as a linear function of joint distribution of the response function variables. So these are the steps they took, and the final result is that the joint distribution of the endogenous variable can be expressed as a linear combination of the joint distribution of the response function variables. Now, using this response function, they express the path-specific counterfactual effect um, by applying this response function variables. So the first term in the PC-Fairnes becomes this, and the second term becomes this. And they next bound the path specific counterfactual effect by solving the following linear programming problem for driving the lower and upper bound. So in conclusion, they developed a general framework for measuring causality-based fairness, and they proposed a unified definition that covers most of previous causality-based fairness notion, namely the path-specific counterfactual fairness, PC-Fairnes. They formulated a linear programming problem to bound the PC-Fairnes, which can produce the tightest possible bounds.